This is geometry, and we are going to talk about inscribed polygons. These are polygons with the vertices on the sides of the circle. In each diagram below, triangle ABC is inscribed, is an inscribed triangle. Right triangles can be inscribed in a circle because the right angle is inscribed in a circle. So we've learned in the past that this would be called an inscribed angle because the vertex is on the side of the circle and the sides come up and touch the edge of the circle. If they come up and touch the edge of the diameter, remember a diameter creates a semicircle, and the inscribed angle has to be half of that intercepted arc. So we know it's a 90-degree angle. So angle CAB is going to be 90 degrees. That's 180 divided by 2. We know the other two angles have to be acute angles, and they have to be complementary. All three angles have to add up to 180. So we're going to say 90 minus 50. ACB, angle ACB is going to be 40 degrees. Now if we talk about the arcs, CAB, from C curving around to A, curving around to B, is half the circle. That's a semicircle, so of course that's 180. And if we're going to be looking at arc AB, that is going to be double the intercepted arc. The arc is double the inscribed angle. The inscribed angle is half the arc. So if we have 40, we're going to times it by 2, and we're going to get an inscribed intercepted arc of 80. We come over to our second one. Again, we have a diameter going all the way across. The only way you can get a right triangle to have all three vertices touched by a circle, so it's inscribed in a circle. The only way to get a right triangle inscribed in a circle is to have the hypotenuse be that diameter. That makes a semicircle, which makes you have that right angle. That means the two acute angles of the right triangle add up to 90. The acute angles of a right triangle are complementary. So that means that half x plus 1/3 x and the 5 have to add up to equal 90 degrees. Okay, this is a little tricky because of the fractions. Well, for us to work with fractions, we need to have common denominators. That means we need to know what numbers 2 and 3 both go into. They both go into 6. So for the 2 to become a 6, we're going to multiply it by 3, so we have to multiply the top of the fraction by 3. So 3 over 6 is the same as a half. Looks good. For the denominator of 3 to become a 6, we have to multiply by 2. So we're going to multiply the top by 2. 2/6. That's the same as 1/3. Now when you have 3/6 and 2/6, that is 5/6. We added our two fractions together. So we can subtract over our 5. Couple different ways we could handle this. I would suggest to multiply the denominator over. That gets us 510. And then we divide by the 5. That gets us 102. So x is 102. And originally we talked about how angle ACB was 90. A right triangle is inscribed in a circle. Well, we've talked about if you have a circle, for a right triangle to be inscribed in that circle, the right triangle has to have a diameter as the hypotenuse, or it has to have a hypotenuse that is the diameter, however you want to phrase that. That's the only way to get a right triangle to be inscribed in a circle. So, since this is a semicircle, half a circle, we know that this angle has to be half of 180. If the radius is 6, what is the hypotenuse going to be? The hypotenuse is going to be twice that 6, because the hypotenuse is the diameter. Okay, next we're going to talk about quadrilaterals. Now notice how a quadrilateral can be inscribed in a circle. Not all quadrilaterals can be inscribed in a circle. Every triangle can be, but not every quadrilateral. A quadrilateral can be inscribed in a circle if and only if the opposite angles are supplementary. So for most all of our examples, we have to do something with supplementary angles. So we know that angle D, this one here, and angle E, this one over there, they're going to be the same total sum as E and G. The opposite angles add up to 180. The opposite angles add up to 180 because they are supplementary. So when we flip over, we probably won't get through every example, but all we have to do is get through a couple examples to see how this is applied. So in this first one, they're asking, determine if this quadrilateral can be inscribed in a circle. Can you fit a circle around that is going to touch all three vertices? Actually, 4. all 4 vertices. And since this one has opposite angles, that are not supplementary, this quadrilateral cannot be inscribed in a circle. Because the opposite angles did not add up to 180. But when we look at this one, we see the opposite angles, 90 plus 90, that makes 180. Opposite angles are supplementary. Yes, this quad can be inscribed. In a circle. That means there is a circle that is going to fit around here. Something like that. And touch all the vertices. This is a trapezoid, that's an isosceles trapezoid. So we know that the base angles are congruent and consecutive interior angles are supplementary. There we have opposite angles being supplementary. Yes, it can be inscribed in a circle, because the opposite angles are supplementary. Now we can come down and practice solving for some of the parts. We're going to do the exact same thing. This quadrilateral is inscribed in a circle. So that means y plus 62 equals 180. Which makes the y value 118. And for the same exact reason, x is 118, because it's the same numbers to calculate. Now here's a tricky one. This one takes you using a little bit of our past experiences with what we're doing now. Notice how this angle x comes around that angle, intercepts this big arc. So we have 170 plus 40, which makes 210. So it's 210 all the way around. So angle x is going to be half of the 210, which is 105. And if x is 105, we know that x plus y have to be supplementary. And we can subtract the 105 over, and we figure out that y is 75. Last one we'll do here, remember, opposite angles are supplementary. So they add together to make 180. Eight goes into 18, actually goes into 16 twice with 2 left over, goes into 24 3 times with 2 8s. Moving down to our next one, we notice that x comes over and touches there and there, which makes that arc. So the angle equals half the intercepted arc of 108 plus 75. So x itself is going to be half of 193. Actually 183, of course. So half of that gives us 91.5. So this is 91.5, which makes z be supplementary with that. So z plus the 91.5 has to add up to 180. So we'll subtract the 91.5 across, and that's going to give us 88.5. And then we know these two opposite angles are going to be supplementary. So we have 2y plus 3y and 5 that add up to 180. So we're solving for y. We divide by 5 to get the y by itself. 5 goes into 17 3 times with 2 left. 5 goes into 25 5 times. All right, last one. We have a star. All the inscribed angles are congruent. Find the measure of an inscribed angle. So we're trying to figure out this inscribed angle. Well, I think if we open this up, we're going to be talking about this arc. And if we extend those sides, we'll be talking about that arc, and that arc, and that arc, and that arc. So it's 360 around the entire circle. That's divided into 5 different pieces. So each of these are 72. So each angle is going to be half of 72. So each of these angles here are inscribed angles, and they're half the measure of the intercepted arc.